so what we got going on, if we're looking at work energy theorem, okay, so the amount of work done is equal to force times distance. Work is also a change in energy, and I think that's what I had kind of gotten to yesterday, yes? All right. So if I want to change the energy of, let's say, a moving vehicle, that means I need to change its kinetic energy, okay? And kinetic energy is calculated by going 1/2 mv squared. Okay, so there would be these two sets of kinetic energy. There would be my final kinetic energy, which of course I would want to be, if I'm trying to stop, how much kinetic energy do I want to have? 0, right. Okay, so this would be 0. I can get rid of it, okay? And that would be my initial kinetic energy, which would have to do with how fast I'm going and how big my car is, okay? These numbers here, this is the force my brakes can exert. This is the stopping distance, which is what we were trying to solve for yesterday. So you guys have gotten to the point where you had seen that if I go twice as fast as I'm supposed to, it's going to take me 4 times as long to stop. Okay? Now, what often people do, okay, and probably all are guilty of it at some point, is to go, 10 over is not a big deal. If I go 40 in a 30 zone, it's only 10 kilometers an hour. It isn't a big deal. Except it is. Okay? It is a big deal because speed is exponentially related to how much energy you have. Any increase in speed causes an exponential change in your energy. That means it goes up lots. Okay? So, if I'm trying to solve for my stopping distance, okay, I would have my kinetic energy that I want to get rid of divided by the force that my brakes can exert. I don't remember what numbers we used yesterday, okay, but we'll do the 30 kilometer an hour one, okay, just to have the number there as a comparison. So we'll go 0.5 times 1,500 kilograms times 8.6, I believe. Squared. Okay, and then we'll divide that by the braking force, which we'll say is 8,000 newtons. All right, so it's going to take me 6.9 meters to stop at the speed limit, okay, of 30 kilometers an hour. I have to have the speed in meters per second when I do energy calculations, just because that's the way it works out. All right, now, if I go 40 kilometers an hour, 40 kilometers an hour is 11.1 meters per second. Okay, don't ask me how I know that, I just do. Okay, so it's 11.1 meters per second. So if I do the same calculation, and now I'm only going 10 kilometers an hour faster, my stopping distance goes from 6.9 meters to 11.6 meters. Okay, it's nearly double. I only increased my speed 25%, but I nearly doubled my stopping distance. Okay, that is a long way if there's a kid in the street. Okay, so 6.9 meters, okay, from my desk is there. That would be a long way if there's a kid in the street. Okay? But if I go 10 kilometers an hour further, or faster, sorry, I'm out in the hallway. That's where the kid is. Yeah? That's a big difference if you're that kid or that kid's parents. Okay? It's a pretty big deal. Okay? For 10 kilometers an hour. Okay? So this is what I ask you to think about. The average school zone, or playground zone, is about 200 meters long. Okay? If you go the speed limit, it will take you 23 seconds to go through that playground zone at the speed limit. You will save 5 seconds by going through that school zone at 40 instead of 30. Those 5 seconds cannot be as important as that child's life. 5 seconds. Now, I actually once had a student try to make this argument with me after making a point. Yeah, but Coder, that's the difference between hitting the red light or the green light at the next stoplight. And I'm like, are you freaking kidding me? Okay, so you're so late that those 5 seconds are more important than the kid's life. But I'll be late. Yep. You'll be really late after you hit that kid. Okay, go the speed limit through very sensitive zones. Okay, school zones, playground zones, construction zones. There's a reason speed fines double in a construction zone. Okay, people are at risk in those places. They're vulnerable in those places. So we need to be more careful in those places. Not that we should speed anytime. I'm not saying we should speed at any point, but especially in those places, we should be mindful and go the exact speed limit, or maybe even a little bit slower. Okay? Because those 5 seconds are just not worth it. Yeah? Point made? Rant over. Okay. Now, onto some fun stuff. Energy. Okay, so in order for work to be done, a force has to be exerted. Okay? When a force is exerted, it's going to cause an acceleration. Okay, in some cases. In other cases, it'll just cause the object to move at a constant velocity. Right? But the acceleration that's produced is actually not just dependent on the force, it's also dependent on the mass. Okay? I mean, think about this. You ever seen a skinny sumo wrestler? Why not? Too easy to get on the floor, actually off out of the circle, right? I mean, sumo wrestling is all about pushing the person out of the circle. So if you're really, really, really big, you're much harder to move because you have lots of mass. It's why you don't see skinny sumo wrestlers. They would be at a serious disadvantage because their small mass would result in massive acceleration, especially if, you know, someone that's 600 pounds is pushing on you and you only weigh 150 pounds. Okay? You will be no problem for them. So in this situation here, okay, if we have this person and they wind up and swing that golf club as hard as they can, they're going to exert a certain amount of force. If they use the golf club properly and hit a golf ball, which has a very, very small mass, they will produce a very, very large acceleration, and the velocity of the ball will increase dramatically. Okay? If they do the same thing, but instead of hitting the ball, they wind up and smoke this truck instead, okay, it's still the same amount of force. They swung the club as hard as they could. But now they're hitting an incredibly large mass. So they're going to produce a very what?
Small acceleration.
A very small acceleration. In reality, is the truck going to go anywhere? I would say destroy the club. Yeah, I don't think there's any hope for that club. Okay, it would be destroyed. No question about it. Okay, and it's very dangerous, by the way, to do that. I used to work at a golf course when I was younger, and one of the other golf courses in our town, a guy got killed because he swung his club at the golf cart, and the shaft snapped, and it came back and got him in the jugular. Blood to death. Yeah, so don't hit stuff with your club. Okay. We also had a guy who hit like 3 balls in a row into the water hazard, and then he took his golf bag, walked up to the water hazard, threw the golf bag into the water hazard, and left. And I'm like, that's crazy. Nobody would do that. And my buddy's like, yeah, you should have seen later. He came back, he went into the water to get his car keys out of the golf bag. Left the golf bag in the water and went back to his car. Like, oh my gosh, he really quit. That's really the end of golf for him. Okay, so if you hit this truck, sure, in the real world, that truck isn't going to move. Okay? But does that mean that you didn't accelerate it? If I'm standing in front of the truck with my hand on the truck, will I know when you hit the truck? Even if I'm wearing noise-canceling headphones, will I know when you hit the truck? Because I'll what? I'll feel the vibration. Well, that means every particle in the truck moved. That counts. That's an acceleration. I may not have got the truck to actually roll or slide, but I still accelerated the truck. Will there likely be a dent where they hit the truck? That also counts. You at least accelerated that part of the truck. That part of the truck has moved. Okay? All of that counts as work. You have transferred energy to the truck. Okay? You exerted a force over a distance. Work was done. Okay? All right. So, motion doesn't just mean the movement of an object from one place to another. It can also mean the change in shape of an object. Okay? So there can be work that does that changes kinetic energy, which would result in acceleration. There can be work that changes gravitational potential energy, that would be lifts something off the ground, and there's work that can change elastic potential energy. Okay, so if I have a spring and I stretch it out, have I done work? Yeah, because what does that spring want to do? If I stretch a spring and I let it go, what will it do? Yeah, it'll go back to its original shape. Same if I compress it, it'll want to go back to its original shape. Okay, that's because when I did that work turned into elastic potential energy in the spring. That means it wants to do work. It wants to let it out. It's the mousetrap example, okay, from before. All right, when you put the lock over the trigger and the killing bar is in place, the spring is loaded. It has elastic potential energy in it because you have changed its shape by loading the trap. Okay, everyone all right with that idea? Okay. All right, so any change in shape can count as work. Okay, any change in velocity requires work. Any change in height requires work, because all of those situations now put some form of energy or change some form of energy about the object or system. Okay, now work and heat, we talked about this on the first day. They are both transfers of energy. Okay, heat is a transfer of what kind of energy? Thermal energy. Work is a transfer of mechanical energy. Okay, so mechanical energy, and we talked about this on the first day as well. Okay, mechanical energy is the total amount of potential energy and kinetic energy possessed by an object. Okay, is it possible for an object to have both of those at the same time? Absolutely. An airplane has both. Okay, as it's flying through the air. It's parked on the tarmac, it does not. But okay, if it's flying through the air, it is above the ground, it has gravitational potential energy, and it's moving, so it has kinetic energy. Okay, everyone all right with that? Okay, so if we're talking about potential energy, in this course we're mostly going to be concerned with gravitational potential energy as our form of potential energy. So gravitational potential energy has to do with three things: mass, gravitational acceleration, and height. Okay? So most of the time, unless you're told otherwise, what value will you plug in for little g? 9.81 meters per second squared. Because we're going to be doing our problem solving on Earth, where that's the value for gravitational acceleration. Okay? So where would you have more gravitational potential energy? Standing 100 meters above the ground on Earth, or 100 meters above the ground on the moon? Where would you have more gravitational potential energy? On Earth. Why?
Because it has a greater
pull or acceleration, exactly. On Earth, G is 9.81. On the moon, it's 1.6. Okay, I could, well, I don't know if I'd want to try it, but if you fell from 100 meters on the moon, it would only be like falling from about 16 meters on Earth. Okay, because your gravitational acceleration is so much less on the moon than it is here. Okay, so falls wouldn't hurt as much. I wouldn't say you'd want to fall from that height on the moon because you'd probably be wearing a spacesuit and you wouldn't want that to rupture. Okay, that was actually the astronauts' main concern when they were on the moon, was not rupturing their suits in any way. It's actually why they had the funny walk that they used. I don't know if anyone ever saw footage of the moon landing, but when they were moving around, they shuffled their feet a lot. Okay, because they found that walking like you do on Earth would actually impart a fair amount of like velocity to them because they were, fit and so much lighter that walking normally produced too much vertical motion and they would stumble, and the last thing they wanted to do was fall and have a rock rip open their suit or hit their faceplate on something and break it, okay, because that could have been catastrophic. Okay? So they actually shuffled to produce more horizontal velocity, because when we walk, we push upwards actually quite a bit. Some people more than others. Okay? You'll never unsee this now when you watch people walk. Okay? But some people walk, I don't know, I think I walk fairly normally. Right? My head stays pretty level. Okay? And some people walk like this. It goes up and down. If you walk like that on the moon, you'll go off the ground, off the ground, off the ground, and you risk stumbling. Okay? All right, so gravity can affect your gravitational potential energy. Okay? Your mass can affect your gravitational potential energy. Okay? So picture this. You're walking down the street and someone says, "Watch out!" and you look up and falling towards you are a tennis ball and a piano. And you can't get out of the way of both of them. Which one do you want to hit you? The tennis ball. Why? What does it have less of? Mass. And as a result, less energy and less ability to do work and change your shape in an undesirable way. Okay? So mass, mass definitely affects how much gravitational potential energy you have. And the height from which you fall, or the height you're perched at, okay, would also affect your gravitational potential energy. Okay? Very few people are afraid of standing on, a chair. But standing on the top of a high mountain is kind of one of those experiences that a lot of people would be terrified of, because, well, we all have this innate understanding that falls are bad. Okay, falling from 1 meter is not likely to be fatal. Okay, but falling from the top of a mountain is. Okay, so there's that height part of the equation. Okay, everybody with me on that? So, if I want to lift something, do I have to do work? I do, okay? Because work, as we talked about before, is a change in mechanical energy. If I'm going to change the potential energy of something by lifting it, that requires me to exert a force through a distance, okay? Because work is also force times distance. Okay, everybody all right with that idea? Okay. What force do I work against when I lift something? Gravity. Okay. This is how you calculate the force of gravity. You're not going to have to do this ever, but this is how you calculate it. So, is that part of this formula? Okay. And is height a vertical distance? So, are this formula and this formula the same thing? They are. It's force times distance. Okay? They have to be the same thing, because if I lift something from the floor to the top of a desk, the amount I change its energy by is equal to the amount of work I did to do it. Okay? That's why the formulas are the same. Okay? If I do 100 joules worth of work, that object now has 100 joules worth of potential energy because I gave it to it by lifting it and putting it there. Okay? Everyone all right with that idea? Okay. If I want to accelerate something, do I also have to do work? If I want to make it go faster, will that require work? It will, and it will require a force to be exerted through a distance, same as if I want to lift something. Okay, it's just the effects are different. Okay, if I exert a force on something through a distance, I can make it go faster, I can make it go higher, okay, or I can change its shape. All of those forms of work can change different forms of energy. Okay, so from a work energy theorem standpoint, these two people are lifting identical blocks to the top of this ramp. Okay? Hercules here on the left is just going to lift the block and set it on top of the ramp. Okay? And this other person is pushing it up a ramp, which is way smarter. Okay? Who does more work? Nope. They do equal amounts of work. Okay, here's why. When this block, and remember, these blocks are identical, so they have the same mass. When they're at the top of the ramp, are they the same height above the ground? And they're both on the same planet, so G would be the same. So it doesn't matter how I get something to the top of that ramp, I do the same amount of work because its change in energy is the same. Regardless of how I get it there, I change its energy by the same amount getting it there. So why do we build ramps then? How do ramps make work easier? Okay, let me ask you this. They do the same amount of work. Who exerts less force? I mean, which is easier, pushing it up the ramp or lifting it?
Pushing it up the ramp.
Pushing it up the ramp. It's the whole reason we invented the ramp. Okay? The ramp is a force multiplier. It means I can do work I wouldn't be able to do directly by having the ramp help me. Okay? So remember that work is force times distance. This person moves the rock a greater distance using less force. This person moves the rock over a smaller distance using more force. Okay? But at the end, the change in energy is the same. Okay? That's why we use the inclined plane, okay, as a simple machine. It allows us to move things we wouldn't otherwise be able to lift. Okay? The plane supports some of the weight and allows us to move the object up the ramp using less force over a greater distance. Okay? This person has to exert a huge amount of force over a much shorter distance. Okay? Does that make sense? That's how the Egyptians built the pyramids. They did not have help from aliens. Okay? They had sand to make ramps and slaves to push things up the ramps. Okay? I'm not saying that's right because it's not, but that's how they did it. Okay? They used big, long sand ramps that would actually wrap around the pyramid. Okay? And as they got done a level, they just add to the ramp. Okay? So they just went around and around the ramp, or around the pyramid, okay, on this ramp until they got to the top. Okay. All right. In this situation, does this system have energy if I'm holding the 5 kilogram ball here? What kind of energy does it have if I'm holding it, not letting it move? It has potential, gravitational potential energy. If I let the ball go, what will happen to the ball? Yeah, it's not a trick question, it'll fall. Okay, when it falls, it'll pull on this block here, yes? Okay, so is some of its potential energy going to be transferred to the block? Does it all stay in the system? It does. Okay? The total energy of this system can't change. It's shared. Even though when this thing starts, the block really doesn't have any energy. It can't fall. It's not moving. Okay? But the ball can fall. When I let it go, the ball will fall, and some of its energy will be used to pull this. Okay? Will it fall at 9.81 when I let it go? No, it won't. Because it's pulling on more mass. That will slow it down. Okay, so it'll try to fall at 9.81, but some of that energy will be transferred to the block, and so it won't fall quite as fast. Okay, so as we were saying here, okay, gravitational potential energy is measured in joules, okay, and just so you know, a joule is a kilogram meters squared per second squared. You will never be asked to write it that way. I'm just letting you know those are the fundamental units of a joule. Okay? We get those by taking mass in kilograms, multiplying it by acceleration in meters per second squared, and then multiplying that again by height. So meters times meters is meters squared times kilograms is kilograms meters squared per second squared. Okay, that's where we get those units from. Okay, so things to remember. Energy is always in joules. In physics, mass is always in kilograms. In chemistry, it's in grams. But in physics, we deal with all kinds of things, from tiny little electrons to supermassive black holes. So we use kilograms for everything. Okay, that is our unit of mass in physics. Okay, G is always going to be in meters per second squared, and unless you're told otherwise, it's 9.81. And height is in meters, because if we don't use these units, we don't get joules. Okay, so mass has to be in kilograms, height and distance have to be in meters, and acceleration in meters per second squared. Okay, questions on that? All right, so if I want to lift a box to 1.5 meters above the ground, okay, can I calculate how much work would have to be done and what its new potential energy would be? Definitely. Okay, so I would know the mass, 3 kilograms. I would know the height, 1.5 meters, and because it specifies that this is Earth, I would know G is 9.81, so I would just use EP equals M times G times H. 3 kilograms times 9.81 times 1.5 gives me 44.1 joules of potential energy. How much work did I do? Okay, so remember, the definition of work is a change in mechanical energy. How much energy did the box have when it was on the ground? None. How much does it have now? 44.1 joules. How much work did I do? 44.1 joules, because work is a change in energy, and I changed the energy of the box by 44.1 joules. Okay, everybody all right with that? Okay, if I was using this, but I wanted to calculate something other than potential energy, like height, for example, okay, then I would have to manipulate this formula, which is super easy to manipulate because, thankfully, everything is just multiplied together. So if I want to move or isolate H, what should I do with M and G? Divide them over to the other side, right? Do the opposite, right? So divide both sides by M times G, and I'm solving for H, okay? Doesn't matter what you need to solve for, you divide everything else off to the other side, okay? So, in this one we have 5,400, so 5,400 joules worth of potential energy. We know the mass of the diver, okay? We assume it's on Earth because we're not told otherwise, okay? So we would plug in our numbers here. The height would be 5,400 joules, okay? Divided by 55 times 9.81, right? And that'll give us that this person is standing atop the 10-meter diving platform. Okay, are those fairly simple calculations to do? Okay. Certainly easier than the acceleration formula. Okay, now, here's the thing about potential energy. It can't actually do any work. It has to be converted, right? I mean, if something is sitting on this desk, it has the potential to do work, but it's not gonna do any work unless it, what? Falls off, right. When it falls off, its potential energy gets turned into what kind? Kinetic. It goes faster. It accelerates towards the floor, okay? So it's kinetic energy that actually does work. Potential energy doesn't do any work. It has the potential to do it, but not going to do it until it's converted to kinetic, okay? Now, if you want to do work and change the kinetic energy of something, you've got to accelerate it, okay? Kinetic energy has to do with a change in speed, right? So, as we were looking at with the playground zone question here, kinetic energy is dependent on two things: mass and speed. Okay? So the heavier something is, the more kinetic energy it will have. And the faster it's going, the more kinetic energy it will have exponentially, because V is squared in this formula. Okay? So any increase in V is amplified by the fact that V is squared in this formula. Okay? Everybody all right with that? Okay. So, I'm going to show you some examples of people doing work with kinetic energy.